Okay, these are the lesson activities for section 2.7. We're going to consider the composite 2D transformation that produces a translation by -1, 4, left 1, up 4, then scales the x-coordinate by a half and the y-coordinate by 3/2. So we're going to visually apply this transformation to just one point, 3, 8. We want to determine where that point 3, 8 ends up after the 3 transformations have been applied. So 3, 8, plot it. And now I'm going to do a translation, left 1, up 4. So left 1, 1, 2, 3, up 4. So that's where it goes next. Then it scales the x-coordinate by a half. So let's see, I'm going to keep track. This was 3, 8. Left 1, up 4 landed me at 2. Oh, I should have paid attention to my scale because those jump by 2. Okay, 3, 8. Left 1 puts me at 2, and then up 4 puts me at 12. Okay, so that's 2, 12. Then scale the x-coordinate by a half, which means my x-coordinate is going to become 1. So I'm going to be at 112. And then scale the y-coordinate by 3/2. So 12 times 1.5 is 18. So I'm going to land at 1, 18. So 3, 8 goes to 212, goes to 112, goes to 118. This is my translation. This is my scale x. This is my scale y. Okay, so visually we can follow a point and figure out where it lands, but I'm going to set up a series of 3x3 matrices that will produce this transformation. In the event that I want to move like 1,000,000 pixels this way, I don't want to do this 1,000,000 times. I'm going to set it up using matrices so that I can just do a quick calculation on a computer to tell me where all the points land. Okay, so the way this works is we use homogeneous coordinates, which means my data point is 3, 8, and we just use a 1 as a placeholder. That's what homogeneous coordinates means. And then I work from the data point you put at the far right, and then you work right to left to set up the transformation matrices. So a translate matrix always has this template. A translate matrix always has this template. You put ones on the diagonal, zeros everywhere except the last column. That's where you put your translation. So my translation is x by -1, y by 4. So I put that first. Okay, my next transformation is to scale the x-coordinate by a half. So what goes in here is these 4 blank boxes. That has to be the standard matrix for a transformation that scales the x-coordinate by a half. And the way you find a standard matrix is you have to determine where the columns of the identity matrix go. So I need to know, to figure out what goes in here, I need to know t of 1, 0 and t of 0, 1 when you're scaling an x-coordinate by a half. So if you scale this x-coordinate by a half, you get a half 0. Scale the 1 by a half, you do nothing to y. And then 0, 1, same thing. Scale the x-coordinate by a half, it doesn't change because it's 0. You do nothing to y. So those are the columns of my standard matrix that go in the blank spots here. So I put 0.5, 0 in the first column and 0, 1 in the second column. Okay, now I do a similar calculation to scale y. I have to figure out where does t of 1, 0 go, and where does t of 0, 1 go when you scale y by 3/2. So in this case, I'm not changing x, I'm just scaling y, and 0 times 3/2 is still 0. And then t of 0, 1, I'm not changing x, I'm scaling y by 3/2, so 1 times 3/2 is 3/2. This is column 1, this is column 2 of the standard matrix for a transformation that scales y by 3/2. That's what goes in those 4 blank spaces. So I have 1, 0, 0, 3/2. And these templates, this like L with the 1 in the corner and zeros elsewhere, that is the template that you always use for a linear transformation. So a scaling, a rotation, a reflection. The only time you use something different is for a translation, because a translation is not a linear transformation. So a translation has a special template matrix. Every other transformation uses this. This zeros and the 1 in the corner always stays the same. All right, so if I were to apply these 3 matrices to the data point 3, 8, I should get 118. So if you actually put these all into your calculator, you should get 118, 1. I'm not going to do it out, but you can test it in your calculator. Call this matrix A, call this matrix B, call this matrix C, call this matrix D, do A times B times C times D, and you should get 118, 1. And the 1 is just the homogeneous coordinate, so the result is 118. Do your answers to A and C match? Yeah, they should. Okay, and one more. We have a 2D transformation that produces a reflection through the x-axis and then rotates 45 degrees about the origin. Visually apply the transformations described to the point 1, 1. Where does it end up after those transformations have been applied? So plot 1, 1. First thing I do is reflect through the x-axis. So I land down at 1, negative 1. Then I'm supposed to rotate 45 degrees about the origin. So picture this as a rigid rod of some kind, and you're going to rotate it up to land on the 45 degrees. It will land on the x-axis at some point, comma 0, right? And I have to figure out what that point is. It's not 1, right? Because the radius is 1 and you're like swinging it up. So we need to figure out what this radius is to figure out where it lands on the x-axis. So I could make a right triangle. So this is 1, this is 1, which means that this hypotenuse is root 2. So this is a root 2 here. So if I write out what I did, I started with 1, 1. I did a reflection about the x-axis, and I landed at 1, negative 1. Then I rotate 45 degrees, and I land at root 2, comma 0. All right, if I want to find the series of 3 by 3 matrices that produce this transformation, just like I did in the last problem, except I didn't give you the templates this time. Okay, so I'm going to have to write that all out. So I start at the right, and I'm going to put my data point, which was 1, 1, and then homogeneous coordinates, I add a 1. Okay, and then I'm going to have a 3 by 3 matrix here. That's the reflection. And another 3 by 3 matrix here that calculates the rotation. So my templates for a reflection, any linear transformation, which is anything other than a translation, always have this template, 0, 0, 1, 0, 0. And then what we have to fill in are these last 4 blocks of a 2x2. So my rotation, that's also linear, so I do 0, 0, 1, 0, 0, and I have to fill in these 2x2 blocks. Okay, so if you reflect about the x-axis, we need to figure out what does a reflection about the x-axis do to 1, 0 and 0, 1. T of 1, 0, when you reflect about the x-axis, if you draw it, here's 1, 0. Reflect on the x-axis, it doesn't move because it's already on the x-axis. T of 0, 1, right, 0, 1 is right here. When you reflect about the x-axis, it lands down here at 0, negative 1. This is column 1 and column 2 of my reflection matrix. So I have 1, 0, 0, negative 1. For my rotation matrix, I have to figure out what happens to 1, 0 and 0, 1 when I rotate 45 degrees about the origin. So T of 1, 0, just going to draw a picture of it. Here's 1, 0. If you rotate 45 degrees about the origin, picture the unit circle. This is root 2 over 2, comma, root 2 over 2. Oh, and I should have written it vertically. And then T of 1, 0, where does that land? If you rotate it 45 degrees about the origin, here's 1, 0. Go 45 degrees this way, you land here. If you, again, picture your unit circle, that is negative root 2 over 2, positive root 2 over 2. So those are column 1 and column 2 of your rotation matrix. So I've got root 2 over 2, root 2 over 2, and negative root 2 over 2, root 2 over 2. Your book uses a formula for rotation matrices that involves sines and cosines of the angle of rotation. You are welcome to use that. I just am terrible at memorizing things, so it's better for me to draw a picture every time. But you can totally use that formula if you feel comfortable with that. Okay, so to apply these matrices to the point 1, 1, you would just multiply. In your calculator, define a 3x3 matrix called A, another one called B, and another one called C. Multiply the 3 together, and you should get 1, 1, 1. I'm sorry. That's the data matrix. You should get the output that we got above, root 2, 0, and then a 1 for the homogeneous coordinates. Do your answers match? Right, they should. Oh, okay, I lied. I thought that was the last one, but we have one more. Consider the composite 2D transformation that produces a rotation 60 degrees about the point 6, 8. So this is, instead of about the origin, we're going about a given point. And then we have a hint that says that means that is equivalent to translating by -6, -8. So you take your point and bring it to the origin, rotate 60 degrees about the origin, and then translate back. So we want to visually apply these 3 transformations, a translation, a rotation, a translate back, to the point 6, 12. So I plot 6, 12, and then it says bring it to the origin. So I'm going to go yeah, okay, so I need to translate by -6, -8. So I'm going to go left 6, down 8. So that brings me to 0, 4, if I translate left 6, down 8. Then I'm going to rotate this point 60 degrees about the origin. So 60 degrees, it's not quite 90, and it helps me to sort of draw a circle, and it's going to land here-ish. It's about 60 degrees. And I have to figure out the coordinates of that point. And then once I have the coordinates of that point, I have to translate it back. Okay, so how am I going to figure out the coordinates of this point? This is, I started at 6, 12. I shifted left 6, down 8, so I landed at 0, 4. So this is 4. And I need to figure out the coordinates of this point. So I know this is 4. I'm going to draw a vertical and a horizontal to make a right triangle. And I know that if this is 60 degrees, then this is 30, which makes this 60. And so I have a 30, 60, 90 right triangle. And I know that in a 30, 60 right triangle, the hypotenuse is always double the short side. So this is 2. And the long side is always the short side times the square root of 3. And then I'm going to put in the appropriate signs. This is left 2, up 2 root 3. Then I have to take that point and move it back by 6, 8. So right 6, up 8. So -2 plus 6 is 4. So I'm going to move it to 4. And then 2 root 3 plus 8. I'm just going to get an approximation for this so I know about where to put it. Okay, so 3. Okay, so 2 root 3 is about 3.5. And I have to move that up 8. So I get 11.5-ish. So I'm going to get 4, 11.5. And if I want to be exact, it is 8 plus 2 root 3 is the y coordinate. So let's write down what we did. So we started with 6, 12. We shifted it by -6, -8. So we went to 0, 4. This was a translate by -6, -8. Then we rotate 60 degrees and we landed at -2, 2 root 3. Again, your book has a formula to figure out where that lands, but I prefer to draw a picture and figure it out. And then we shift back. We do another translate by 6, 8. And that puts you at 4, 8 plus 2 root 3. So if we want to find the series of 3 by 3 matrices that produces this transformation, I'm going to start with my data matrix, 6, 12, and I'm going to write it with homogeneous coordinates. And then I'm going to have a translation. Then I'm going to rotate. Then I'm going to translate back. Okay, so my translation, my translate matrix template has 1s on the diagonal, 0s everywhere except here and here. And that's where you put your translation. But I'm going to fill in my templates first. My rotation matrix is a linear transformation. So it has the zero, it has the L template with a 1 in the lower right and zeros forming that L. And then I have to fill in these 4 boxes. And then I have another translate matrix, same template. Okay, now I'm going to fill in. The translates are easy. This one's -6, -8. This one is 6, 8. And then the rotation one, I have to figure out by determining where does 1, 0 and where does 0, 1 land when you rotate them by 60 degrees. So I need a little bit more room to do that. Move down here. So T of 1, 0. If you rotate 1, 0, 60 degrees, draw a little picture. Here's 1, 0. 60 degrees lands you about right here. That's on the unit circle. And I believe it is 1/2 √3/2. And then T of 0, 1, where does that land when you rotate it 60 degrees? So here's 0, 1, rotate 60 degrees. That is on the unit circle. And I believe it is -√3/2 1/2. You can always pull out your unit circle and look at this too, just to make sure. I'm just going by my memory of the unit circle. We use it so often that it's good to just sort of have a picture of it in your head. Okay, so those are going to be my column 1 and column 2 of the rotation matrix. Your book has a formula for figuring out those 4 boxes that uses sines and cosines of 60 degrees. Welcome to use that. I prefer to draw the picture. So to apply the matrices, you would multiply this matrix times this matrix times this matrix times this matrix, and you should get where we landed earlier. You should get 4, 8 plus 2√3, which is approximately 11.5. Your calculator will give you a decimal, 1. And if you do that calculation, it should match where we landed up here.